Hello, hello, hello. So you recently saw a video of an eddy current break, which is kind of cool. And it consisted of an aluminum disc and a magnetic field. And I wanted to take a couple of minutes to talk a little bit about the theory behind what was going on. So as was pointed out at the time, aluminum is not a magnetizable material, but it is a metal, which means that you can get current to flow in it. You have free electrons. So here, let me get my little pointer. So what I want to do is I want to define a little circuit that I'm going to identify with a little circle here, and we're gonna track what's going to happen to that little circuit as this disk rotates into and out of this magnetic field. So clearly there's metal out here and there's metal internal to the little circuit, but all I'm interested in is what's happening in this little section here. And obviously this is idealized, but just kind of go with it. So at this particular point, the little circuit doesn't have any magnetic flux through it, and there's no changing magnetic flux, so there's no induced current in it. If it proceeds, though, to move into the magnetic field, what you're going to end up having at this point is a changing magnetic flux. And you know from Faraday's law that when you have a changing magnetic flux, it's going to induce an EMF, which is going to induce a current. Lenz's law allows you to identify the direction of the current. So if you go through the Lenz's law steps, direction of the external magnetic field is into the page. The magnetic flux is increasing, which means the induced magnetic field has to be opposite the direction of the external magnetic field. So how does your hand have to curl to be able to accommodate a magnetic field that is going to be opposite? And so you want the external field is going this way, you want the induced field to go this way, which means apparently that the current has to flow like so, which means you're going to get current flowing like in that direction, like so. So that's what? In the counterclockwise direction. Okay? Now, what's interesting and what's important here is that the part of our little coil that is in the magnetic field that has this induced current flowing, that induced current is going to end up interacting with that external magnetic field. It's going to feel a force a la, IL cross B. I mean, it's like a current carrying wire in a magnetic field. And so if you do the operation, the current's flowing this way, the magnetic field is this way, the force is going to be up. And so this little guy is going to end up feeling a force that's going to be upward. As time proceeds, my little circuit's going to end up getting itself into the middle of this magnetic field. And at that point in time, there isn't going to be any changing magnetic flux, so you're not going to end up having any actual induced current. I've got to get rid of my picture for this next part. And then what's going to happen is, that the little circuit is going to try to exit. And when it tries to exit, what's going to happen is now you have a changing magnetic flux. Once again, Faraday's law kicks in, induced EMF, induced current. Lenz's law lets you deduce what's going on with the induced current. So direction of the external field is into the page. Magnetic flux is diminishing, which means the induced current has to be in the same direction as the external magnetic flux. To be able to get a current in that direction, that current's going to have to end up flowing, clockwise. And again, you can go through the little right hand rule. You've lost my picture here, so you can't see me do it, but you saw me do it in the previous section, and you can see how that would work out. You should be able to do that. The point, once again, though, is that now you have this current that's flowing. If you use IL cross B on it, once again, you're going to end up with a force, and the direction of the force is going to be upward. So in both these cases, as our little circuit is either going into the magnetic field or going out of the magnetic field, you're going to end up having this force being applied to it. And then obviously once this guy completely gets out of the magnetic field, then everything goes back to normal. There's no induced current, there's no force, no nothing. So taking a look at this kind of holistically, clearly this thing that we're looking at here is not just a little circuit. It's actually a continuous piece of aluminum. And so metal is constantly moving into this magnetic field, and it's constantly moving out of this magnetic field. And as it does, charge carriers will be swirling at this boundary. And as they do, they will be interacting with this magnetic field, feeling a force that's up. And charge carriers at this boundary will be swirling. And as they do, they will end up interacting, producing a force up. Okay, this swirling, those are the eddy currents. Okay, that's where the eddy current part of this system comes from. And the breaking phenomena that occurs due to the fact that you constantly have eddy currents at this boundary, or at these boundaries, and you constantly have these forces that are fighting what's going on, that breaking phenomena is what creates what we call an eddy current break. So as I pointed out in the video, these things are used in high-speed trains. Apparently the newer versions of the high-speed trains, given the fact that the energy in these breaks gets dissipated generally as heat. And so they finally came up with kind of an engineering coup and figured out how to take that energy and convert it into usable energy. And so they don't just use straight eddy current brakes anymore on trains. Apparently now they have these sort of like regenerative brakes where the energy is actually captured and stored to be used later. But in any case, the point is that the principle is the same. Interestingly, what was it called? Full Throttle ride at Magic Mountain, it stops with an eddy current brake. Next time you're there, if you take a look at the area where the carts actually come to rest, you will notice that there are copper plates in the area where the carts come in to stop. And so it's basically an eddy current brake that stops them. Anyway, so that's how these things work. And that's all I have to say. So have a good day. Keep smiling. Life could be worse.